Welcome back, everyone. It's my pleasure to continue this conference with Victor Holanda from CSCS. Victor.
Yes. So, thank you. I am just starting after lunch, so you're basically a bit tired, so let's try to wake you up. So before I actually jump into the results and jump into the projects, let's try to put a bit in context what we are doing here. We are working with denyroot, a tool to try to confine users in HPC systems. And it's good to step back and put into context, right? So I will try to give you a bit of the context why you're doing that. So it gives the impression that we're not headless chickens at least, right? So on security, there is this idea that you have a framework for doing security that's called NIST, that's cybersecurity framework. And it starts by having a government, like a governing body that does security governance. And then you do identity, you identify assets, then you protect those assets, then you detect threats, then you respond, and then you recover, right? So the point is that today in the morning, you saw Massimo present something related to Marmot graph that goes in the direction of identity. So you want to identify all the assets at CSCS, try to correlate and get them, being able to act upon any threat we find. So then we protect those assets, right? So there's a work that we have been doing and has been published already on CUG, the Cray User Group meeting last year. And then today, I will be talking about a part of the work that we're doing that goes into detect and respond. So we want to detect threats and then respond to them. And of course, if you want to see the full thing put all together, how the things all work, so then you're going to come this afternoon to Mateus Basso's talk, where he's going to talk about how you operationalize all of this into security, right? So basically, this is not my work. This is a CSCS team building teamwork, right? So we are using this opportunity to do everything all together. So this work is a fantastic work and very challenging. And the reason why it's challenging is because I tried my best to slow down CSCS systems and I couldn't. So if you look at the results of the tool that we have written, basically the numbers are all the same, right? So the performance impact of having denyroot on HPC is virtually zero. The change is 0.006% for trying to spam exec calls. So basically, I'm trying to span multiple processes and forking from different processes. So the p-value that you see there tries to find out that with and without denyroot is that we can distinguish the two sets. And the toast, it means that basically we can prove that these two sets are the same. So that's not only does not affect synthetic benchmark, but also in practice, it doesn't affect also scientific simulations. So the results that you see from GROMACS show that basically we cannot distinguish. And I had to make an effort. So the previous results, we had to run 2,000 times to be able to see some difference, to see, in quotes, differences, right, to be able to compute. And then in GROMACS, we had to run a few times to find out those values, right? Of course, these results, the benchmark that I'm showing you, are not all. Basically, these are the worst numbers I got. Literally. So this tool basically has no performance impact. So we are trying to bring back the P insecurity from HPC. So where does this tool fit, right, on this detect aspect and response aspect? So if you imagine that you're going to go into a CSCS system, right, a user is going to connect. What does it mean if you're using SSH? You basically go through a gateway node called Ella, and then you jump into our systems through login nodes, and you can submit jobs and interact with everybody, right? At CSCS, we have other ways to go inside. So we have Jupyter Hub, so we can actually interact with the systems via Jupyter. We also have Firecrest, so you can do RESTful APIs. And then the point is that, we have some bad guys, right, trying to go into our systems. That's reality. And then they try to attack our login nodes and jump into our gateway nodes and jump to a login node. But so the way that we do that is basically by doing, separation. You do network segregation. You put firewalls. You put gateway, API gateways. You do a bunch of those controls. But, the fact is, and also you do more than just protecting the network side. We also do protect title, protect identity. We put MFA for the users. And then this is amazing, right? But the fact is that, if you only do that, we are driving blindly. You need to know when things happen. So we also have to put some sort of centralized logging. So we actually collect logs from the systems, and then we can act upon and find out if you have been attacked or not. But then the issue is that this collection of logs, they need a team of people to be able to process them, right? You need to have people doing actually screening and understanding of those logs and standard threads. So a better would be if the guy gets inside, right, because it eventually gets inside, because we have no perfect protection, right, is that this response that the team has to do doesn't have to be manual, right, has automated. Right? In security context, basically it's called SOA, Security Automation, Orchestration, and Automatic Response. And then at CSCS, what we want to do by doing that is actually take the guy out of our systems with the minimal impact, decreasing the blast radius. Basically, that's the idea, right? So we do have security. We protect the perimeter. We do our best with MFA. We try the best to avoid that the guy will come. But eventually, no systems this is not an air-gapped system. So then we want to be able to respond to those threats, protect against those threats in a way that's, doesn't require a huge team of people. So how do we do that, right? From collecting all those logs and responding, that's the key thing to be able to respond automatically, right? So when the nodes start to send their data to the central log, we can do basically the centralized response, or we could do this local response on the node. And then for the infrastructure, as you saw today from Massimo's talk, we have a bunch of tools. The vendors provide different logging mechanisms. So there we are kind of well covered. For the OS, the same. You tend to have all those IPS systems, and you collect logs, and you collect system logs, and you can get logs from Slurm and so forth. But the problem happens is about applications running, right? So if the guy is inside, he's not going to be inside just to do nothing. He's going to execute commands, right? And then that's where the problem arises, at least in HPC context, right? Because there are basically two good mechanisms in Linux to basically get what the people are running. One is called audit the process in the Linux, the subsystem, audit subsystem, and eBPF, which is a fairly new technology in the kernel. It's from 2015. For a kernel that starts in the 90s, having a technology that starts in 2015 is an early one. So what are the challenges, right? We care about getting the P in HPC, right? We care about performance. And then if we do audit, we observe that there's a slowdown on the performance of applications. Just by enabling auditing of tasks, which basically enabling auditing of executed commands, the MPI applications just go down, they slow down naturally, right? So what are the reasons? So why does the kernel decides to slow down your MPI applications if you turn on task auditing? It's basically because they use a buffer and they do locking on every message they do on the audit subsystem. So, which means that you have like a bunch of MPI applications try to write or read a file, then the audit subsystem will make it those parallel reads and writes become serial by locking mechanism. So we also have the disk overhead, because everything that you do in audit goes into a file, right? So there's no API that you actually can probe an audit system. And then there's also the problem that if you start to write very fast with the audit subsystem, it will freeze if you reach the buffer. So if you start to write very fast, every single operation will be frozen by the audit subsystem until you can clear the buffer. So this slows down even more if you're doing multi-MPI applications, multi-rigs, like at scale. And then there's also the networking overhead, because when you do centralized monitoring, we actually have to take those logs out of the system and send, and audit generates a lot of logs, right? And that will affect our MPI traffic. And the worst, in my opinion, is that audit is rule-based. So what does audit mean? That you write a rule, and then that rule is stored in a rule table, and then if an operation happens, then it goes through the rules and tries to see if the rules matches that operation, and then suddenly, boom, it executes or doesn't execute, which also adds a bunch of cycles. So audit has its problems. So what do we want? What would be ideal on HPC? The first thing is that, we don't want to have locks, or at least decrease the amount of locks as possible, so we can actually run a lot of stuff in parallel. Another thing is that we maybe don't want to write events to disk. We know infrastructure is not so generic that we have to write to a file and then, collect that file. We can actually send directly to the central system without having to write to disk. We can bypass this OpenNet call that happens on the kernel. Then we want also to decrease the number of events. I maybe don't want to get all the tasks. Maybe I shouldn't be monitoring. I don't care in security point of view if the guy is running a Gromax MPI application. I actually want to find out if he's doing something bad. And another thing is that if I collect all the commands being executed in the system, I have a very low signal-to ratio, right? That's a problem. So it's going to be a bunch of noise. I'll be collecting a bunch of data, and I have to find that nail in this big stack, right? And then most likely, we should change the mechanism from doing this rule-based, where you have to screen through the rules, to something different. And because the kernel is written in C, basically the option is to do a callback mechanism first, maybe, right? That's the idea. So what's the other option? Since we have audit, and the other one we chose to use eBPF, right? So at CSCS, we have been choosing lately to do all our logging via eBPF. But wait, Victor, CSCS didn't invent eBPF, right? I didn't invent this concept. There's a reason why eBPF was invented in the first place, so people know about it. So this is not a new idea. That's actually true. There are many tools in the market doing exactly that, right? Using eBPF to monitor what's happening, right? So what they do, basically, they have an automated response software, right? Those tools. And then when a program executes, it uses eBPF, which they make a syscall, right? It's a callback-based mechanism where you have hooks written in the kernel. There are places where the kernel developers add hooks, and then you just attach callbacks into those vtables from those hooks, right? Basically, that's the idea, right? And then if they find something that matches some sort of rule, they go there and kill it, right? That's the idea, basically. And these tools already do it. So what's new about what you're trying to achieve versus what the people are already doing? So, the problem is that at HPC, we do thousands of syscalls per second. So again, the signal-to-noise ratio is very small if I start to look at only syscalls, right, or any syscall. But since those tools are written generically, right, for protecting any IT device, that maybe that's not the best approach for our HPC environment. So our preliminary results show that we have like 11% slowdown in some workflows. And of course, I have to put like a bunch of grains of salt on this result, because I by no means an expert in any of those tools, right? I try to install them, I try to run them, and try to put them to work, then I was systematically getting slower results. Maybe an expert on those tools would be able to, speed up, but I personally was not able. So you should take those results of getting slowed down with a grain of salt, right, on it. So the idea is that we know we need to not measure only any syscall, we need to measure something different, like that's basically the idea. What is the something different we need to measure? The point is that, if I want to have access to CSCS, do I really care if a racket got inside and started running Gromax? Maybe not, right? I really, really, really care if the guy goes and becomes root in my system. And if the guy goes and attempts to become another user and then starts to steal data from that user. Basically, that's let's say, the higher problematic, higher impact we have. Of course, for running GROMAX, we have another project that's, we have another colleague working on that also, Jana, which is called YALT, where we try to identify what people use so we can identify those outliers like, Bitcoin mining and so forth. So then the idea is that we will looking at these credential transitions. So I will try to look at from the point of view that the user will try to become root without being able to, or without being allowed to, right? And then we have seen a lot of vulnerabilities on the Linux kernel associated to that, right? Where you can privilege escalate. So then we will be looking or monitoring exactly that path in the kernel. And then what happens then? If a process starts in the Linux kernel, basically you make a new process. Every process requires credentials. So the Linux kernel will make a call and can be set as UID, can be reset as UID, and then they will make a call in the kernel called prepare credentials, prepare creds. And then after that, the Linux kernel people, actually NSA wrote it, when they start to develop the SE Linux, the LSM, the Linux Security Module, one of them, they added hooks along the kernel, and that's called LSM hooks. One is called Security Prepare Creds, right? And then these hooks used by SE Linux, for instance, to block if a process you're allowed to run or not a process. This is also used by other modules, but SE Linux the most, the one that used the most, this one. And then if it passes this hook, if there is a check and the check passes, then the kernel creates the new credentials in practice, updates the credentials into the application that's called commit credentials. And you may also intersect that call, and then there is another hook from the security that calls security commit creds. And then after that, after the process has been spawned, has a new credential committed and so forth, it's able to run. Basically, and you move on with the stack on the kernel, how to security allocate, resources and so forth, blah, 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 blah. That happens. So what's the genius idea we had? Well, let's copy SE Linux. Let's hook here. Literally, that's basically the brilliant idea behind this entire project, right? So instead of implementing SE Linux, complete SE Linux, we are just going to do the same thing that SE Linux does. And why is this important? It's because it's not only enabling SE Linux that you need to do. You need to do enabling SE Linux, and you need to do something more that my engineers hate, and every engineer that I've met hates. So how does it look like, right? If you have a system where you have denyroot enabled, but SE Linux is disabled, basically, and you try to do sudo, and you're not allowed to sudo, for instance, so which means I cannot able to change credentials, then the program will basically block. Right? And also I try to change my user, try to impersonate another one, the system will also block. Right? That's the idea. But what happens if I have SE Linux enabled? Right? What would happen if I have this thing and SE Linux? Well, if you have SE Linux enabled, you see it's enforcing, then you do sudo -i, and then it's blocked exactly the same way. And if you have denyroot disabled and SE Linux enabled, basically, it's the same operation. It's the same error you get, right? Because we are doing exactly on the same point in time, exactly in the same place. Of course, for implementation details, the eBPF hooks happen before to run before the SE Linux hook, so we block before, right? Basically, that's the idea. Then the thing is that, how did you achieve that? Did you only look at the hook? No, because in practice, what happened is that to have that LSM hook, being able to hook it to it, your kernel has to be configured with a boot parameter saying LSM equal to BPF. And that's not always true for every single computer we have at CSCS. Of course, I can make a request, or I can make a pull request to a repository and change those parameters. I have done that for a lot of them. But what happens in case you can't do that for a given reason, because a given vendor doesn't do that, or some particular system you cannot touch the boot parameters? So then we propose to do a two-path mechanisms. So the user starts a process, right? So then the kernel credentials, the kernel does things to get the credentials. Then if it's the LSM module is enabled, the BPF1 is enabled, then I can not only synchronously stop at that moment in time, but I can also do the rest that's required, right, for logging. I can, send the data that someone attempted to do a transition that was not allowed. I can also add other responses to it other than just blocking, like you do in SC Linux. I can kill the user section. I can kill every other program that the user is running. I can block the user from logging in. I can send emails. I can Slack. I can do a lot of stuff. That's what we do, right? But in case the BPF module, the LSM BPF module is not enabled, what can I do? Well, I can trace as every other tool does on this area, which is not so great for security, but we could. Then it's actually take the right path, which is basically I'm going to be started tracing syscalls again, and then do all of these. So we have mimicked everything that the other tools do, but we have the better path on the left that allows us to block in a performant way. Right? Of course, Victor, sounds great. So why hasn't all the tools done that, right? Why they haven't done that? Well, because taking the right path, taking the path for tracing is more generic. I can do much more with the right path than I can do on the left path, right? But that's all? That's really all it? No, there's other limitations too. So it basically looking only at credential transitions, right? Today, the Linux kernel, if you go to CV details, has around 14,445 CVs open, right? So it's not a very safe product, let's put it this way. And out of those 14,000 and something CVEs, around 225 were related to privilege escalation, right? So despite the fact it has a lot of issues, some of them have high impact. And out of those 225, basically 30% are related to credentials transitions, right? So this tool doesn't cover all the cases. It only covers the cases of the credential transitions, right? Which is okay for us at this point in time. So if I can manipulate the kernel in another way, well, I won't be able to block it. And those cases are basically arbitrary code execution. If I have, like the CLW, the cow issue we had a few years ago, that one's are basically I can change the memory in the kernel, so then I wouldn't be able to block it. But also it doesn't block if an application has already been allowed to. So imagine that you have a pseudo CVE that or vulnerability that as you do sudo ls, and this ls takes forever, and then there's a vulnerability on the ls, but this ls has is already running as root, and someone attacks that ls, I cannot block anymore because the transition already happened when the sudo command was emitted, right? So it is not the perfect bullet, but guess what? The last one is not solved also by any other approach that we take. Right? So to fix the previous two top points, we added that right path, the path that you do basically the tracing also. But that path has to be enabled with care, let's put it this way, right? Because it may affect performance. So this is all, literally, but of course, only looking at credential transitions is, how can I say, limited. So there are other things that we care about at CSCS. So we haven't released the version of the code yet, but we want also to do capabilities transitions because some applications they require increased capabilities, especially when you are doing things like mounting a container, mounting a file system, getting the network transition and so forth for some of these runtimes. We also want to do username space transition control. So, the kernel has some interesting username space vulnerabilities where someone is running in a given username space, I can jump into that username space. And it has been, solved, some of them, but, it's very interesting, those stuff. These are not privilege escalation as root, but it's a privilege escalation as users, right? Because root in general has its own username space codes, right? So then the idea that we want to do also is that Can we reuse those tools and improve them so that I don't have to support this new denyroot? That's basically one of the things we want to see. We are doing this because some of the systems we cannot do SE Linux, but as soon as I can do SE Linux everywhere, the tool loses its importance, right? Even though it can be used incrementally to SE Linux. And also, better would be if the tools on the market could already do credential transitions, capability transitions, and use the space, and they could turn off everything else they do, because they basically don't care about the Kubernetes type of workflows that they run, right? They care about. So what's denyroot in practice? What's the take-home message? If you haven't looked at your laptop all the time and haven't paid attention, this is the moment to pay attention, okay? Basically, this is a tool that prevents kernel transition, credential transitions, right? With a very small overhead. The maximum overhead we saw was 0.25% in the kernel, and I had to run over and over to be able to see it, right? Can be deployed as a standalone, or can be added together with another security control, which is basically SE Linux, right? Also together, if you're using a system that's based on Debian and also on Ubuntu, you don't have SE Linux, so then you should install this, because app armor doesn't protect you against privilege escalation at all, right? So you should mount your file systems that the user writes to as no SUID and add this thing. Then it's based on eBPF. So I haven't gone into a lot of details about eBPF, what it means in practice in the Linux kernel, but it's a mechanism that we can do sandbox applications. So even if I have a flaw on my eBPF application, I cannot allocate memory, I cannot sleep, I cannot do a bunch of stuff. And then it can be deployed into two modes. An enforcing mode where I actually block, I cannot allow you to move forward. So your blast ratio is basically minimal if you have a vulnerability. But I also can do monitoring where I attack your system, then the response comes back. The response time, I haven't gotten details of the code, but the response time that we have selected today is 10 milliseconds. So if you go faster than 10 milliseconds, then you know you're going to beat me. But in production, when you go to production, it's going to be smaller. So you have to be very fast, right? By the way, the good thing about the Linux or the bad at the same time is that everything in Linux is a file, which means that if I spawn a process, I have to do an opennet syscall. By doing opennet syscall, I'm already faster than 10 milliseconds. You're already slower than 10 milliseconds. So that's the reason why you got 10 milliseconds, right? So it's going to be very difficult for you to beat 10 milliseconds because everything's a file. In Linux, you know, the entire interface is a file. So with that, I tell you that, you know, thank you very much. And if you have questions, let me know. I'm open for questions now, and also outside I can give you more details on what's the, you know, this beautiful, amazing tool that's impossible to create noise on your system. So thank you.
Thank you, Victor. Any questions?
Thank you. You mentioned about 10 milliseconds, but whenever you have a compute system like Alps,
Yeah.
so have you estimated or benchmark times to lock down something within 1,000 or 2,000 or 3,000 nodes?
No, so this 10 milliseconds is not the time to is the time that the Linux kernel takes for doing the loop, right, of starting, going to all these credential things, mounting the file systems, getting the network stack enabled for your application, and then execute your applications, right? So in our systems, it's true that if you're doing some particular use cases, you're going to get faster than 10 milliseconds, but those particular paths that you don't have network, you don't have storage, then I don't care so much about doing transitions because you cannot escalate privilege so much. Unless there's a particular path in the kernel, and those paths, I don't care so much. But increasing from 10 milliseconds to 1 millisecond, it's the same, right? I mean, just to change code, and because the ratio between signal to noise is very small, then I can, you know, I can afford that cost.
Was there another question? Okay, thank you, Victor.
Thank you very much.
Monday.